I do my job well. Okay.
Yeah.
Yeah. Yeah. All right.
Too well.
Okay. I'm desperately trying to get us out of definitions into some meat. See, is there anything else I need to talk about? No, I don't need to talk about that. Okay, let's do a step towards meat problems. And what I mean, something we can sink our teeth into. 4.2 is going to be fun. Nowhere near as much fun as 4.6.
What's your definition of fun?
You know what my definition of fun is. Normally involves pain for you guys. All right. So if I have a second order homogeneous linear DE, how many answers should there be? Two. I like it. So we got this one? Oh, you good? Okay. So if I know one of the answers, this is what I kind of teased last time. If I know one of the answers, maybe I can try to use that known answer to get another answer. Now, what I need you to understand is I have to do this now before we get into the first real, full, just find all the solution, you don't know shit method, because part of that relies on what we do with this. So people are often like, why do we learn this? You got to know how do I find that first solution? It's just given to us. Well, what if I'm supposed to have two answers? I can only find one of them using the process. I need to use this process to get the second one. I mean, so we need to know this process going in. So this is called reduction of order. Now, just the title implies what's going to happen. I mean, I have a second order DE. I know an answer. This kind of should make sense that using the answer, I can do what? Reduce the orders from a second order to a first order DE, and that's going to have one answer I can find directly. There you go. The title tells you what it's going to do. It doesn't tell you how. So let's say I have a DE, second order, linear, homogeneous DE with y1 of x as one solution. All right, so the method to use to find the second solution using the first solution, and this is really, really freaking neat. You guys, again, sort of related to my definition of fun, maybe. What's got to be true if and there is a y2, what's got to be true about y2 and y1 have to be what? You can do it? In order for them to be a true family, a fundamental set of solutions, they have to be independent. Which means that one cannot be in this case there's only two of them, so one can't be a multiple of the other, a constant multiple. So one must be a functional multiple of the other one. Does that scare you? It can't be y equals 2 times y1. Maybe it's y equals x times y1. Maybe it's y equals natural log of x times y1. Right? They just can't be constant multiples of each other. Right? Give me, here's x. Give me something that's linearly independent from it. X squared. Right? Oh, somebody said that. I think somebody did. What's the matter?
You said x squared was linear independent of x.
Of course it is. What do you, no. What do you, again, linearly independent means one is a constant multiple of the other. So that's why this one is okay, right? So x and x squared, isn't x squared just x times x?
Yeah.
All right. And I don't care. Anything you come up with. What about x and sinh of x? Are they independent?
Yes.
Oh, hell yeah, I'm not going to prove that shit either. They're freaking independent, right? So isn't this x times sinh of x divided by x? I mean, at that level, it feels like, well, yeah, Jeff, but what the shit? But we don't know going in what the other thing is. We're just saying, I know it's a functional multiple of the other one. And then I can use that in the original DE to kind of reduce its order. If I make a substitution, it's going to do that for me. All right, let's do a concrete example. Okay, because hopefully you understand what I'm saying is this. I would say y, the solution, it's got to be some multiple, functional multiple of the other guy. Because to be linearly dependent means that one divided by the other one is a constant. So if I make it a function, then they are independent, as long as the function is not constant. Okay. And then I would do derivatives from here, do substitution like we always do. It really, at the heart of it, is just a substitution process, a well-informed substitution process. All right, let's try a concrete example. And then I got a little handout for you guys. Thanks for that. I don't know why I thought about Python. I knew there's something. It's number 7, I think, in the book. So let's see. 9 y double prime plus 12. Where'd it go? There it is. Minus 12, sorry. 12y prime plus 4y equals 0. So one solution is this. Where'd it go? That's one solution. Let's do this one together. Makes sense, Jeff, because they don't know what the hell they're doing yet.
Very true.
So I'm going to assume that this y, equals some functional multiple. I'm not going to write all the of x's, okay? So this would be, I'm going to assume that y equals x, gather x. I just said it was u e to the 2/3 x, where u is a function of x, right? That's a funky. Okay, now you just take all the appropriate derivatives. So you can imagine what we're creating here is if I had a third order, I'd need to know 2, and I could figure out the third order.
Since the u is a function of x, we use particle in this, right?
You got it. So what's, this should feel very familiar. This is sort of like an extended, you sort of see the connection between the homogeneous, chapter 2 homogeneous. Isn't that where you say y equals ux? Mm-hmm. All right? Oh, interesting. There's a connection. This is y equals u times whatever y1 is. So y prime, u prime,
Plus 2
okay, y double prime. I try to do, so u double prime, e to 2/3 x, right? Then you're going to get, u prime times this guy prime, right? Let me see if you guys see what I'm saying. U prime is equal to this with a prime line. Let me see. U prime, let's just do it, Jeff. U prime times 2/3 e to the 2/3 x, right? But then don't you get 2/3 u prime e to the 2/3 x right there? Do you guys see what I'm saying? Because now this is here. This is started here. One more term to go. Plus 2/3 u double prime. Okay, now notice to save yourself a lot of writing. This is homogeneous. There's a y everywhere in the DE, right? Some y piece. Are you with me? What's going to happen to all the e to the 2/3 x's?
Factor out.
I could divide both sides by them because they're never 0. Are you guys with me? So you got to be careful to do this if your function you're working with isn't that way. But you can at least factor it out. But in this case, I can just kill the damn shit. So I have to write less. So if you're one of those people that have trouble, yes?
Why is the last term u double?
I don't know why. That's a really good question. It should not be. Thank you for bringing that up.
Shouldn't it be 4? Is it 4/9?
4/9. There it is. I don't know where I was coming from. Thank you. Please keep me straight on those things. Appreciate it. So now you just throw stuff in here. So what I'm saying is don't write any of the e to the 2/3 stuff down. If you need to, do it and then kill it. I don't want to waste time in the first place. So it'll be 9 times, so I get 9 u double prime plus 18, so 6, 12, what is it? 3, 6, you got it, Jeff. 6 u prime plus, I never noticed it, I never showed you. Those were like terms. That's what I was trying to say. You can kind of put them together as you go. And then I just decided to never put them together. So I do get 12. Is that cool? So this is the term I'm working on right now. Plus 4u e to the 2/3 x. Now I can start to line up like terms. Minus 12 times y prime. Is that cool? Because it's 9 times all those parts. Oh, get out of there. Thank you. I'm trying to read y. Are you looking at me weird? Because I just made a mistake. I said you might. Minus 12 times y prime. So I get minus 12u prime. Is that cool? And I'm not writing the e to the 2/3 x's, hopefully, because that's all going to cancel. Minus 12 times 2/3 is 8, so minus 8u. And then I finally get plus 4u equals 0. Is that cool? There's 9y double prime, there's 12y prime, negative 12y prime, and there's 4y. With all the e to the 2/3 canceled. You can even cross through them here if you wanted to, you know? Or you can put them all in there and then kill them. It's up to you. What happens here?
Cancels out.
Yeah, this doesn't always happen. At least these terms are going to die. And maybe you can see why. Some of you guys are like, you didn't reduce the order at all, Jeff, because this is still...
9
Now, in general, this term could stay alive. In which case, I'm going to do this. I'm going to do this step anyway, even though we really don't have to here. And is it cool? I can kill the 9. Poor little 9 just wants to die. So watch this. I can let w equal u prime, so then w prime equals u double prime. That is what you do in general. If one of these stays alive, you definitely want to do that for yourself. So it doesn't reduce the order like itself. We come in and realize if these all die, I could step the order here down 1. And that's really building on the knowledge you have that anytime I take a derivative, I make a new function in its own right. So u prime is its own function. They're separated by a derivative. So on this one, you guys realize I didn't have to do that blue? Not a big deal. But if I do, what w prime equals 0, so what's w? Ah. C, let's tell them, C1. Guys, if w prime is 0, integrate.
Yeah.
So w is C1. What was w? U prime. Now integrate. U is C1x plus C2. I like it. All right, let me stop there for a second. In general, you're going to have to do this step because then what you end up with is a linear. If one of these is still alive, it would be linear in W. When these die, that's beautiful. You really don't have to do this step. Now, what was U? Or in this case, how do I use U? Let me say that. That's a better way to say it. How do I use U? How do I get Y? I multiply what I found by this. We stop here for a second. Y is, and what's Y? What's Y? That is the magical answer, right? Why we have part of the answer. I want the whole freaking answer. That's what Y is. What did we just figure out? We figured out the multiple, the functional multiple I want to use on e to the 2/3 x. So what do you get when you use it? I get y equals c1x plus c2 times this. So I get c1x e to the 2/3 x plus c2 e to the 2/3 x. Now there's some slight variations on this where you don't get the whole answer. I really like doing it this way because you get the whole answer at the end. You don't have to put them back together. But this is y1. Can somebody tell me what y2 is? It's in there.
It's C1x.
It's just x e to the 2/3 x. I like it. There's y1. There's y2. I know the c's are, so just deal with it. So let me give you this handout. You got to understand that this process is actually very nice. it ends up with either something that you can integrate twice directly, or it's linear at worst in W. I have a little example on here. By the way, guys, I don't know if you remember this. Now, real quick, here's reduction of order, section 4.2. Obviously, down here you can see the title. This is from section 4.3. This is the one I gave you a little preview about a while back, and it's related to this problem. Do you guys remember what we did with this before to actually solve it? You let y equal, what function is related to its own derivative, so it's like terms? E to the mx. You don't have to actually worry about the constant coefficient because that's going to get thrown on at the end. When you plug this stuff in, I don't know if you guys remember this. You guys got this here, right? Okay. When you throw this in, when you take a derivative, you get m e to the mx. When you take another derivative, you get m squared e to the mx. All of these have e to the mx in them. So that would cancel. So I end up with 9m squared minus 12m plus 4 equals 0. How do you factor this? Especially when these are squares. This is 3 squared, this is 2 squared. 3 times 2 is 6, doubled is 12. All right, so that's going to be 3m minus 2.
3m minus 2.
So you get m equals 2/3 twice. But the answer can't be e to the 2/3 x twice because is that independent from itself? So desperately not. One multiple. 1. Oh, shit. You guys understand? So what's really neat is if you do this and you get repeats, the reduction of order tells us all I've got to do is multiply it by x, and that makes an independent, linearly independent second solution. That is really flippin' cool. And this would be on the handout I just gave you. It's case 2. Underneath homogeneous linear DEs with constant coefficients. You see how this is a homogeneous linear with constant coefficients. That's section 4.3. Yes?
So do that first. If it's the same, just add an x to it.
Yeah, if I get repeated roots,
Okay.
so that shows up twice. So it really looks like there's just one answer. Then one answer is going to be e to the 2/3, and the other one it's x, and the other is going to be x e to the 2/3 x. So if I got m equals 7 and 7, one answer would be e to the 7x, the other one's x e to the 7x. It's real. Yes, sir.
And is that only true with e to the x as the function, or?
No, it's true in general. When you do section 4.2 homework, I wanted to do one more example of 4.2 before we really move into 4.3. And you guys are like, oh, we got plenty of time. Based on what I normally have when I look up there. Let's do one more example in 4.2 that's not this form. It's not one we've talked about yet. Just for kicks. Let's see what happens. And when I say let's, I actually mean you. So here we go. Everybody got what they want from up here? Probably more than you wanted. Okay. So still in 4.2. Let's do, yeah, that looks gross. Let's do this one. That's not too gross. Let's do that one. That's not too bad. Everybody out there's like, pick a homework problem. Come on, Jeff. There's a chance because I don't remember what the hell I assigned. Now notice, I want you to notice something about this DE. This can't be E. Can't have an answer like E to the something because you've got these x multipliers. So why does x squared work? Because what's the derivative of x squared? 2x, then times x is still x squared. So it's like terms, and then this fills in the powers I lost through differentiation. Do you guys see that? So when they have these like decreasing powers of x coefficient type things, then the answer is going to be some type of polynomial in an x cubed, x squared, x, you know. Maybe. You don't have to know all that yet. That's coming, I can't remember what section it's in. But all I want you to do is the reduction of order process we just did. That's all. So assume what y looks like based off of that y1, just like we did a minute ago. Okay, there we go. Sorry. We got everybody doing something good. All right, let me start to catch up to you guys here. Oh, there you go. I'm still creeping. Is that what you guys got for those?
Yeah.
All right. Then So you see, there's nothing here to divide by, so you're just going to work with everything. So you get x fourth double prime plus prime x cubed plus 2ux squared plus 2x, so you get 2u prime x cubed plus 4x squared u minus 6ux squared, right? Now, equals 0. And again, real quick, I don't know if you guys, I think a few of you guys do this. You can always, right here, you can immediately build what you need and then throw them together instead of like relying on your memory and eyeballs, right? So you just do it immediately. So right here you could say 2xy prime and then 2x times 2x. You guys see what I'm saying? And then throw them in. Whatever works better. Some of you guys, no matter what I say, you're like this. So here, so remember what I said. This term has got to go away so that you're left with the derivative terms, and then you can make a substitution and make it linear at worst, right? So thankfully these do. If these don't go away, you made a mistake over there somewhere. Is that cool? Those go away. So then I can say, so I got x4u double prime plus 6u prime x cubed equals 0.
So it's right so far.
And if I say, I don't think this problem said this. Where did I get this problem from? Who knows, Jeff? Oh, yeah, 4-2.
What'd you do in the second line there?
There it is. There it is. Where are we at?
In the second line, the plus 2u
Oh,
prime.
so this is x squared times y double prime. This is 2x times y prime.
Okay.
Yeah. So that's what I mean. Right here next to this, maybe it's better to write this, and then you can work right off of this. So I think some of you guys do that, which is smart. I don't know. I'm a certain kind of smart. You guys can be smarter. Now tell me, why am I allowed to divide by x cubed here?
Because it's the same.
From the beginning, I knew that x
Was it
cannot be 0. Okay, so I'm allowed to divide by x cubed because I know it's not 0. Or, you know, even better, I can divide by x to the 4th because then I can see what? What is this? Now do your W step, which some of you guys are not going to do, and I don't blame you that much, but it just makes it a little bit. So if I say W equals U prime, W prime equals U double prime, and now I've got it linear in W. How do I solve this? Put it up here. Oh, and you could say, I don't know how I would solve it. How would you solve it, Jeff? Show me. What's the important part here? This is linear, so yeah, p of x. So e to the integral, let me rewrite it up here. E to the integral 6 over x. So it's going to be e to the 6 ln of x, which ends up being x to the 6. So a lot of you guys are going to be able to see that and go straight to this, which means I do what? Yeah. Multiply by x to 6. If you notice this is in some other form that you want to do, you can do that. And so this is now what? X to the 6? 7. Yeah, good. You guys, everybody still kind of with me? I mean, if you're up here with me, you're golden. You should know the rest of this stuff. Yes? Where is it? Here?
Yeah.
Yes.
Okay.
It's not, son of Jarrell. No, it's a 5. It's not S. Yes.
So between
x to the fourth u double prime, blah, blah, blah. And then the next step, you just divide it by x to the fourth.
Yeah,
Okay.
exactly. Why did I do that? So then I can put it in true linear form. I like it. Oh, here, true linear form. So this will be x to the 6w equals c1. So then w equals c1 over x to the 6th. W is u prime. So what's u? Am I integrating or differentiating? Integrating, because I'm going from prime to not. And when I integrate, the power goes up by 1. C1x to the negative 5th divided by negative 5. That's the part that you can throw out if you just want the second answer. Because that plus C2 is a multiple that will pick up this guy. Do you guys? If you don't see what I'm saying, then don't worry about it. Just do that. So, again, whenever I get to U, that is what I multiply the one I knew by to make both of them show up, both the answers. So if I multiply, now I take, multiply this by x squared, I get negative 1/5 c1 x to the negative 3 plus c2 x squared. What's up? Is that all right? You guys see that? So what's y2? If they ask for specifically y2? Yeah, negative 1/5 x to the negative 3rd. I like it. Oh, wow, shit. All right. Guess you probably are happy I can't show you one more thing. Obviously, next time we're going to talk more especially about case 3. And you might want to, I can't remember if I wore this shirt for you yet or not, but the e to the, what's Euler's? More specifically, e to the pi theta plus 1 equals 0. You guys ever learned that this is like a rotation? So if I rotate 180 degrees, if I start at 1 and I rotate 180 degrees, where am I? Negative 1. And what's negative 1 plus 1?
0.
Why did I put theta? E to the I pi. I love you, Jeff. You're awesome. So pi is like, this is a way to represent a rotation.
So I is just the...
Which is really what I is. I itself is a half rotation, and that's why it's a square root. This is a half rotation. That's enough of that, sorry. I would highly recommend you look at this. E to the I theta equals cosine theta plus I sine theta. Does that sound familiar? Yeah. All right. We're going to talk a little bit about that next time. Cool. I'll see you then. Yes?
Can you just absorb the